stimulus to our perception of it. And a way of thinking about sensation and perception, again, these are terms that are in italics, so nothing you have to spit back out in an exam, but a way of feeling about that is you feel a pebble in your shoe. You feel the actual pushing or the pressure, right, or even possibly the pain. And the perception is, oh, that's a pebble in my shoe. And then, of course, your final result would be to go and take your shoe off and take the pebble out. So you have the sensation of the pressure and the perception of discomfort, for one example. Or, again, response to remove your shoe, remove the pebble. Then we talk about sensation at three different levels: the receptor, the circuit, and the perceptual level. And this is background, just to give you a general idea. But this just gives you a general idea we talked about before, where you have the original receptor, wherever that may be. It may be your fingertips, or it may be in your eye for vision, wherever that may be. That sensory receptor is picking up a stimulus, whatever that may be. And then it's using the ascending pathways, which we call the circuit level, to carry that information up to our brain, or wherever we're going, in the spinal cord in some cases, we can have a perception of that, an understanding of that, the perceptual level. So we have receptor, circuit, and perceptual level. Now, it talks here a lot about, this idea of perception. This is just some of the one picture, for example, they show you in your textbook, which is not a bad example of how you can do this. This is an experiment we're not going to do in this class, but it makes you understand. Think about it this way: high definition television. We have very, very high, sharp picture, almost looks real, because we have so many little pixels, right, in a very small area. Now think back to 1950s television, where you had a very, let's say, very unclear picture compared to what we have today. It's still vision, it's still light that you're seeing. It's just that the amount of light, the number of particles, gives you higher sensitivity, or at least it has improved receptive fields. And this is just one example of how you can do this on your skin. So you can take a needle, or two needles really, and you can poke it on your skin, and you can, let's say you poke them a good inch apart on your hand, you can feel too. So your hand has the ability to distinguish those two pricks as being separate. But at some point, if you get those closer and closer together, you're only going to feel one. So you have limitations, and parts of your body are different. So you can see on your hand, you have a very small receptive field. You can tell changes, very, very small amount of changes, versus on your back, which is a little harder to tell. So your body, again, has been built in different ways because it uses its hands to respond more to the external stimuli. It needs a smaller receptive field. Makes sense in general. It's just what I'm going for here. Okay? And again, all this isn't just in italics, just to give you an idea. Of course, this information is taken up, as I said, through various circuits we described before, and ultimately up to the cerebral cortex, which we interpret those stimuli, or we perceive them to be whatever they may be. Pricks on the finger, color red, an orange we're smelling, etc., etc. Okay? We'll talk later on about this idea called adaptation. Adaptation, we'll come back. Some of our sensations adapt. In other words, for example, think about your eyes. All right? You're in a movie theater. It's dark, right? And then you go outside, and it's really, really bright and sunny. As soon as you walk out of that theater, especially if you go out the exits at the back of the theater and go right outside, you practically feel blind. You can't see at all. Because your eyes have acclimated, right, or adapted to the dark situation. When you go out in the light, your eyes are quite literally overwhelmed. Okay? The opposite would be true if you came from a very bright room and you went into a dark one. You can't see very well. It takes time to adapt. So some of our responses, some of our stimuli adapt. Vision is one of those that's very easy to tell. Okay? Other things don't adapt. For example, pain, we'll talk about later on. Our bodies are designed not to adapt to pain, because pain serves a very important function. Okay? We don't want to have reduced pain. We want the stimulus to still be there. And we may cut the lines along the way, but at least at the level of the receptor, we won't have adaptation. We talked about first, second, and third order neurons already, so that just talks about the circuit level. The only thing I'll mention here, just on page 3, again, it's just some background information, something I'm never going to test you on, but it just gives you an idea of, the amount of information that we can perceive from various receptors. For example, if you look here, we can understand, one, that a stimulus has even occurred. We've been pricked in the finger, for example, or we're touching something, we feel something, right? We can also detect how intense it is. Is it hard, soft, for example? Patterns, spatial things. Can we see a pattern? Can we find a feature? So if we touch velvet, for example, velvet has a very distinctive feel to it versus satin or cotton, for example. Quality. We'll talk about qualities later on, but something that's bitter, something that's salty. Okay, this gives us what we call quality discrimination, and it is pattern recognition. We can see someone's face. So a lot of these can come into play. Again, just some background information against Luna Taux. Okay, something that we will get to on an exam, and that starts at page 4. We're going to classify receptors, sensory receptors, in 2 different ways. Now you can classify sensory receptors by the stimulus type, the type of stimulus. For example, we have touch, or pressure, or vibration, stretch, or itch. These are receptors that are specifically designed for these purposes. They're itch receptors, pressure receptors, okay, in your skin, for example, or touch. These respond to mechanical stimuli, so we call those mechanical or mechanoreceptors. And so you can imagine, as an example, if my hand is representing a neuron, my fingertips are the dendrites, the receptors would be here on my fingers, and if I touched it, that mechanical touching would open up the channel, leading to sodium fluxes, going to, in this case, the axon hillock. Okay, so the mechanical touching, pressure, itch, whatever the neuron is designed for, is what's going to lead to the ultimate action potential for that neuron. Thermoreceptors respond to changes in temperature. So again, go back to the same scenario. Now your receptors on your dendrites are going to respond to changes in temperature. Okay, so if all of a sudden you touch a hot object, that receptor is going to respond. The stimuli is temperature. So you're going to feel that because it's going to fire that neuron, and your brain is going to interpret that firing of the neuron as heat or cold. Okay? Thermoreceptors. Photoreceptors respond to light energy. So for example, in your eye, we'll talk about in the retina of your eye, we have photoreceptors. Again, the same thing. Go back to this. We have a receptor. It responds to a photon of light, and it fires if it receives that right photon. We'll talk about the properties of light and vision in just a little bit. Okay? Chemoreceptors respond to chemicals. So they could respond, for example, they could be a channel for hydrogen, H+, or the hydronium ion. Okay? It's one possibility. Or they could have a channel for sodium. And so again, you have your dendrites, and they have those receptors on there. And if the amount of sodium goes up in the environment, the sodium is going to go through those channels, get picked up by the neuron, it's going to fire. Why would that be? Well, salt. Salty foods. How do you taste salt? The receptors in your tongue pick up sodium. How do you detect acids? You pick up hydronium ions. H+, that's a proton. Proton donor is an acid. Okay? So we can detect these changes by the receptors, or the design of the receptors, again, on the dendrites of those neurons. And then nociceptors are pain. Nociceptors are pain. So they detect pain. So those are the 5 ways to classify them by stimulus type. Something you should be aware of. You can also classify them by location. So we have receptors that are on the outside of the body, or specifically they respond to stimuli outside the body. They're not necessarily outside the body, but they respond to stimuli outside the body. So you typically find them on the body surface, and not always so. So touch, pressure, pain, temperature, and also the special senses we'll talk about later on. So things like vision and hearing, equilibrium, taste, and smell all fall under what we call exteroceptors, or respond to stimuli outside the body. We also can classify them as interoceptors. They respond to changes inside the body. And there's a lot of things you have to respond to. You'll learn in 102 that the body has to sense pH in the blood. Right? You have to detect that and respond to that. So there's going to be all kinds of changes that can occur within the body chemistry, for example, that have to be monitored. And there are receptors, again, the same kind of idea, that are going to be on the dendrites that are going to respond to those stimuli from the internal environment. So you're hungry, you're thirsty, okay? Or you feel internal pain or things like that would be considered an interoceptor. Proprioceptor is a special case where, again, you're responding to body position. So your connective tissue coverings of bones and muscles, you have proprioceptors. And this is what sends information up to the cerebellum and tells the cerebellum this is the body's position. Remember we talked about the cerebellum giving the instructions to the primary motor cortex to how this is how you're going to walk. This is the current position of the body. This is how you're going to walk. So it has to know the current position. Proprioceptors do that. Then you can also classify them by distribution. And this is one that we'll spend the rest of our time on. And we just kind of say, okay, well, we have the general ones and we have the special ones. Okay. The general ones is anything but the special ones. Anything. Okay? So we have our general receptors for pain, etc., or pressure, or touch in the fingertips and things like that. We would consider that a general sense. The special senses are 5 in particular we're going to focus on. Okay? We call them the special senses. Vision, hearing, equilibrium, smell, and taste. And we're going to get to those in just a few minutes. But yes, you should know all 5 and be able to spit those back out. Okay? As far as your general receptors, these are just your general receptors in your body, not the special senses. So not hearing, okay, not tasting, not balance, and smelling, I think is the last one. Okay? These are the other ones. So what would you find in your fingertips, for example? Well, you're going to have pressure, you're going to have touch, you're going to have other ways to distinguish between velvet and cotton. Right? You're going to be able to sense some pain, some very, very deep pressure possibly. And so we're going to have different types of general receptors. Now some of these receptors are naked and some of them are encapsulated. Meaning there's an actual capsule or cell that surrounds them. So that's simple as I'll make it. Simple as it has to be. Okay? So we have what's called unencapsulated nerve endings and we have encapsulated nerve endings. So again, the same thing goes back to this. You have a dendrite, right? Cell body, the dendrite sticking out. Some of these are wrapped up and some of these are not. Simple as that. So you can have free nerve endings right here that would be, for example, in the skin, or some of them are wrapped around a cell we call a tactile cell and make a tactile disc, or some other ones are even wrapped up more than that where you have what's called a corpuscle for pressure and things like that. I'm going to leave it simple. I'm not going to complicate it. You don't need to know all these. I don't really care. But if you've seen in your lab book, for example, you're labeling things like Pacinian corpuscles and free nerve endings, things like that, that's all this is. They all fall under a general receptor, general sensory receptor, and I'll leave it at that. Okay. Special senses, bottom of page 5. Again, your special senses include taste, smell, hearing, equilibrium, and vision. And I believe we're going to cover it in that order. Okay? Vision will take us longer than most of them. Hearing being the second longest, I would imagine. Okay? Let's go ahead and do each of these in turn. So the first two we'll talk about are chemical senses. Taste and smell respond to chemicals. Okay? Now, these terms gustation and olfaction you should be familiar with. Gustation is another term for taste. Olfaction is another term for smell. So the olfactory pathway or the gustatory pathways, you should be able to know, describe. Olfactory would be smell, gustation would be taste. tasting. We have the ability to taste or detect roughly 10,000 different tastes, I guess you'd say. Okay? I'm sorry, we have 10,000 different taste buds, to detect 4 or 5 different tastes. And we're actually going to call 5 in this class, I'm sorry. 10,000 different taste buds. Each one of these buds is designed very similarly, and you're going to basically think about it along this line. Okay? So this gives you a very small picture of what you see here on the tongue. By the way, anybody ever heard that you taste more salt here or more sugar here? Wrong. Not true. Okay? Your taste buds are relatively evenly distributed throughout your tongue. So you have salt and taste and umami. We'll talk about those. Bitter. They're relatively distributed around the tongue. I don't think the whole mapping thing that we always learned in elementary school is even correct. I think it's one of those urban legends like cow tipping. You can't do that either, by the way. Okay. You guys watch Big Bang? Okay. Didn't watch Big Bang, get that. Okay. So taste buds, as I said, there's roughly 10,000 different taste buds, and each of these is designed to detect a particular taste. We'll talk about those in just a few minutes. But this is the general design of that. So we have a gustatory cell or hair here, which you just call a taste hair. And those taste hairs are where the receptors are. So the receptors are located right in those hairs, and that's what's actually going to taste the food. Now the food is going to be dissolved in saliva and then go into this little pore right here. They call it a taste pore. So in order for you to taste anything, it has to be dissolved. It has to dissolve in saliva. It has to be water soluble. If it is not dissolved in water, you will not taste it. Not possible. Okay? You'll see this true with smelling as well. If you can't dissolve it, you can't taste it. You can't smell it. Okay? So once it gets dissolved in saliva, then it can go into this taste pore, one of 10,000 different pores, and possibly stimulate one of the receptors that's on these taste cells. So this one right here may be designed to taste bitter, or sour, or sweet, or umami. Okay, and we'll talk about those. It responds in these taste cells and then sends a stimulus over here to the brain. So the 5 basic taste sensations. Okay? Sweet, salty, sour, bitter, and umami. You should know those 5. Okay? So the salty one makes sense. So let's say we eat something salty. Well, what's going to happen? Well, sodium chloride, sodium. We're going to have a lot of sodium in our saliva. Well, that's going to get picked up by those hairs. The sodium is going to go in, lead to these cells having an action potential, leading to transmission of saltiness to the brain. And we're going to perceive that as being salty. Same thing with acid. Channels, again, receptors in the taste hairs will respond to acids in that way. Bitter, we have responses to things like quinine or other things like nicotine, which we perceive as being bitter, and we can respond to that. The other tastes, though, are pretty much done through G protein coupled receptors, which we didn't get into. But in general, you kind of think about this being a receptor right here, and it's going to respond to a very specific stimulus. So this might be sugar, for example. Okay, and it'll bind to this pocket right here, and that will eventually lead to rise in calcium, and it will eventually lead to an action potential. So again, you have receptors designed to pick up sugar, or receptors designed to pick up glutamate, which we'll talk about glutamate in just a few minutes. But again, this is all G protein coupled. It's kind of complicated. I told you we're going to skip it. But in the end, it leads to the same thing. It leads to an action potential. So no matter what the stimulus is, whether it be sweet, salty, sour, bitter, or umami, in that case glutamate, we're going to have the same response. We're going to have an action potential that's going to go to the brain, and whatever that labeled line is, this is going to go to the brain and say, that's bitter, that's salty, that's sweet. Now, what is umami? People are always like, what is umami? Well, It's a relatively newer term. It's Japanese and it refers to tasty. So meaty, brothy. You've probably heard of it most often with monosodium glutamate, or MSG. You ever heard of MSG? MSG, or monosodium glutamate, is a taste enhancer. What does that mean? Well, what happens to food when you put salt on it?
It gets salty.
It gets salty, but what else does it do? It gives it flavor. It's more than just saltiness. You ever put salt in watermelon? Not too much. It incredibly adds to the flavor. Okay, so you don't want to add too much to make it too salty, but you can add salt and it's a flavor enhancer. The same thing is true for MSG. It's a flavor enhancer. So you can add it to foods to make it meatier, more savory. Now there are some people out there that don't believe it's a good thing. There are also some people out there that don't believe salt is a good thing. So people say don't put MSG in food. A lot of Chinese restaurants do it even today. So other ones say no MSG. But they don't have MSG, by the way, they have salt. They have one of the two. So, okay, so that's what that is. Umami is basically meaty or savory, and it's glutamate. It's an amino acid that our body has a specific receptor for. We pick up that glutamate and we respond to it with a perception of savory or meaty. Okay, it probably wouldn't surprise you that taste is 80% smell. If you ever had a cold, you notice that your taste perceptions went down. You couldn't taste things that all tasted the same. And you really need to have smell to really enjoy the world around us with respect to taste. There are some other things as well, though. Thermoreceptors respond to temperature. Mechanical receptors respond to the actual physicalness, or the mechanical, is it tough, is it squishy, or whatever the case may be, right? Nociceptors, pain. So temperature, pain, and all these other things actually add to flavor. Some people really like spicy food. That's painful, right? But some people really like it, like myself, Think about mashed potatoes, right? Mashed potatoes, you leave them out in the room for a while. Hot mashed potatoes versus cold mashed potatoes. There's a big difference in the taste, isn't there? It's not just one's colder. It just doesn't taste as good, right? There's a lot of things that go into this. Think about broccoli. Cooked broccoli versus raw broccoli. Carrots. Cooked carrots versus raw carrots. People won't eat one versus the other. I can eat cooked broccoli, not raw. I can eat raw carrots, but not cooked. It's one of those funny things. Yeah.
I've seen people who have lost some people who have lost their sense of smell will really pour on like the hot sauce.
Yep.
Because they're trying to get something to be. Otherwise, it's hard for them to eat because they just lose their appetite.
Yeah. Yeah. Some people say they don't like onions because they don't like the texture of onions, things like that. So there's a lot that plays a role in here than just our five senses. That's my point.
Is it true that you train your palate?
Train your palate.
Yeah, people said you can train your palate to like for instance, not that I like it, but beer. It's a.
You mean it's an acquired taste?
Right. Well, I've heard.
I'm not sure if that's much of at the level of the receptor, is it's more of a perception in your brain.
Do they mature? Like, you like things when you're older that you didn't when you were
They do.
Or you don't like things that when
But again, I don't know how much of that is at the receptor level and how much of it is at the
Is
perception
like
level.
a conditioning.
Yeah.
Is it true that your taste buds change every 7 years?
I've never heard that.
I've heard that before. Like, you try it in 7 years, you might like it then.
Again,
I'll forget about that.
from the basic design and the receptor, I don't think there's a difference. But again, how we perceive it. I mean, you think about the food you ate as a kid versus as an adult. I mean, kids, for example, really, really like bitter and really, really like sour foods. Like the Sour Patch Kids are a huge hit for kids. Adults, not so much. Why is that? I don't know. Okay, some people go against the grain and like raw broccoli, but not all of us. Right, Nicole? And not all of us. Okay. So the rest of it here, I'm going to skip over. I went over what I wanted to go over here. So let's go to the second. Smell. This is where the 10,000 comes in. So we have about 10,000 different odorants that we can detect, roughly. I mean, I don't know if anybody would really count that. So we have receptors, again, that we can pick up roughly 10,000 different odorants. Well, we have a mucosal layer right here. When we inhale, we breathe in. We are breathing in odorants, chemicals that are in the air. And those chemicals will get lodged and stuck in that olfactory mucosa, the mucus there. And if it can dissolve in that olfactory mucosa, then it should hopefully respond and cause a response here at stimuli level, causing those neurons to fire. So this is giving you a big picture of what this is here, which you've already looked at with the sheep, the olfactory tract, and this gives you another level to actually show you the level of the mucosa. So you can imagine airflow coming in. Here is different odorants are going to get stuck in that mucosal layer. We're going to have all these little hairs. Each one of those will be designed to pick up one specific odorant. And once it responds, it'll send up the signal to all these different cell types, which we're not going to get into, neutrophil cells and others. But the overall result is we end up going to the brain, and we perceive that as different types of odors. Good, bad, and ugly.
Should we know these pictures?
No. There's nothing here. No. Nope, none of these will be on your exam. Or this one. Okay. As I said, just like when you were talking about taste, smell has to be dissolved. You have to have the odorant dissolve in this case, the mucosal layer to actually smell it. When you talk about all this, we talked about olfactory tracts before. Olfactory bulb is just the part that looks like a little bulb here. So we go through all that. That's all I really want you to know. Simple, right? This just shows you, in case you're curious, how incredibly complicated odor can really be. Because we have our direct connection here, which is going to tell you, are you smelling something sweet? Or are you smelling something foul? Are you smelling something rotten? Or something very pleasant? Right? We're going to perceive all those from multiple stimuli. But we also are very well connected to different parts of the limbic system. So we're going to smell a skunk and go, oh my gosh, right? Maybe you ever had a skunk really close? Okay. If it smells like burning tires, you know you hit a skunk roasted. The normal smell of skunk is actually after it's dissipated. If you smell burning tires, run. That means it's right next to you. So, but that sense of caution and danger and emotion with smelling a skunk, especially if you're walking around and you see a black and white cat, right?
Yeah. Here, kitty.
Limbic system, exactly. It's probably not Pepe Le Pew. Or probably is Pepe Le Pew, right? Okay. Next one here we're going to be talking about is the ear. Now, the ear actually encompasses two different senses. And the second one people often forget. So we're going to be talking about hearing and also equilibrium, or balance. Now, we use equilibrium to do a couple of things. One, it tells us our body position. Are we standing up? In normal space, for example, with gravity pulling this way, are we standing up? Are we laying down? Are we upside down? Right? How can we perceive our body position in space? That's one of the things that equilibrium does. It also tells us angular motion. Are we moving? Left, right, forward, backward, up, down in an elevator. Are we moving? You can feel acceleration. And that's really what you're feeling, is acceleration. Okay? So if you're riding an elevator and you've started, and let's say you've been going for 3 or 4 floors, you're going up to 20, you probably don't feel it anymore, other than maybe just a little bit of vibration. You're not feeling you going up anymore. You only feel that at the beginning, right? That acceleration is felt at the beginning. And when you get to the top, you slow down, you feel it. So all really acceleration is a change in speed. So you accelerate, or you go up and down and accelerate. Okay, so we call that angular